Welcome to the Dev Journal. We are exploring the growing tension between the sophisticated beauty of new research models and the chaotic reality of production environments. As artificial intelligence moves from experimental code to autonomous agent fleets, the industry is colliding with significant security vulnerabilities and the high-stakes financial costs of coordinating these complex digital systems. We are starting with a look at Google DeepMind and their unified Latents framework, which has just achieved a new state-of-the-art for video generation. It is a stunning piece of engineering that brings us closer to high-fidelity synthetic media, but it also raises difficult questions about the infrastructure required to support such heavy compute loads. Beyond the models, we are seeing a dangerous exposure of credentials within Google Cloud that could lead to massive billing risks for developers. It makes the dream of autonomous systems look like an expensive liability. But Vance, you have been looking at the specific ways these agents are being exploited locally, right?
It is actually worse because the ClawJacked flaw demonstrates how easily a malicious website can hijack a local session. We are also tracking the technical complexity of building asynchronous trading bots using the latest Python frameworks. We will start today with the architectural shift in video generation and why it is hitting a wall of security risks.
DeepMind just pushed the boundaries of video generation with their new unified Latents framework, achieving a state-of-the-art 1.3 Frechet video distance score on the Kinetic 600 dataset, which represents a significant leap in visual fidelity that makes synthetic media feel less like a dream and more like a reality. What stands out to me is the near-perfect reconstruction they have achieved using a fixed Gaussian noise encoding at a log signal to noise ratio of 5. A level of technical precision suggesting that the artifacts of early generation are finally becoming a thing of the past for high-end digital production environments. The framework also introduces a deterministic encoder that predicts a single clean latent rather than drifting through probabilities, which creates a more stable and predictable model architecture that could finally provide the reliable foundation creators need when they are trying to scale digital assets across massive enterprise projects or complex marketing campaigns. It feels like we are finally seeing the bridge between pure research and actual utility. But I am curious if the underlying math is as smooth as the output looks. So Vance, how does this approach to training efficiency actually stack up against the benchmarks we have seen from other major models recently?
If you look at the ImageNet 512 benchmark, the efficiency is actually quite impressive because reaching a 1.4 Frechet inception distance and a 30.1 peak signal-to-noise ratio, while outperforming both diffusion transformer and EDM2 in training compute, is a massive victory. The secret sauce here is how they simplified the callback labeler term in the evidence lower bound into a weighted mean squared error over noise levels, which allowed them to jointly learn latents in the first stage, and then freeze the encoder and decoder to scale the base model while maximizing hardware performance. I do have reservations about the assumption that these latents are perfectly optimized from the start, because while forward noising the predicted clean latent is a clever trick to ensure the representations work for reconstruction, freezing that architecture so early might limit the model if the underlying data distribution shifts significantly during scaling. Even with those concerns, the jump in efficiency shows we are getting much better at squeezing performance out of individual nodes, which is essential as we transition from the foundational model layer to the orchestration layer, where multiple agents use these models to build software in the reflectt-node coordination system.
The way we think about team composition is changing rapidly with systems like the reflectt-node coordination framework. By running a local representational state transfer application, programming interface at localhost port 4445. This setup allows a team of 9 autonomous artificial intelligence agents to build software products in a fully synchronized environment. What I find most compelling for smaller development teams is the speed of implementation for this kind of high-level coordination. You can actually have these agents self-install and join the active loop in under 5 minutes just by reading a Bootstrap uniform resource locator at reflectt.ai/bootstrap, which lowers the barrier significantly. This framework mimics a human peer review process through automated collision detection, where a third agent identifies and flags duplicate efforts on the same file before merge conflicts occur. It then takes post-task reflections and clusters them into actionable insights to resolve recurring system issues like permission errors, which provides a level of maturity we rarely see. I believe we are seeing a shift toward a more organic way of managing digital labor by treating these agents as a cohesive unit rather than isolated tools. I am curious, though, if the speed of the initial setup masks any underlying complexity in how the system actually maintains its memory. So Vance, how does the state management work?
While the 5-second Docker deployment using the latest image from the GitHub container registry is undeniably fast, the real engineering depth lies in the move away from linear execution. The system relies on stateful management through a shared task board and persistent memory, which allows the entire team of 9 agents to maintain context across complex development cycles. I have some concerns regarding the overhead required for that third agent to monitor every file interaction for potential collisions. While it prevents immediate merge conflicts, you are essentially dedicating a significant portion of your compute just to watch other agents work, which might create a bottleneck if the coordination loop experiences any significant latency during heavy production loads. There is also a non-zero risk that if the coordination loop itself fails, you could end up with corrupted file states across the entire project because the agents are operating so closely together. Relying on automated reflection to fix permission errors or architectural drifting assumes the agents can always correctly interpret the state of the shared task board. We have to consider that as we give these autonomous agents more control over our local environments through open protocols, we open new doors for exploitation. This leads us directly into a major security concern, where the same local coordination that makes these tools powerful can be hijacked by malicious websites through the newly discovered ClawJacked vulnerability.
This new ClawJacked vulnerability is particularly terrifying because it exploits the very trust we place in our local machines. By using cross-origin WebSockets, malicious websites can essentially hijack your local OpenClaw agents. It turns a helpful productivity tool into a direct gateway for remote attackers to gain administrative-level permissions without any warning. What makes this so dangerous is how the local connections bypass the standard security prompts we usually rely on for protection. When these agents are operating in the background, they assume any request from the local host is legitimate. This flaw allows a simple visit to a compromised website to compromise your entire local development environment in seconds. We are also seeing a major breach of trust within the ClawHub ecosystem itself, where over 70 malicious entries have already been identified. One specific skill named Bob P2P Beta is actively targeting Solana wallet private keys. It is a stark reminder that even the extensions we download for our agents need rigorous vetting.
Sloan, the technical breakdown of that February 26th patch for version 2026.2.25 reveals why this was so easy to exploit. The developers completely missed a rate-limiting mechanism in the gateway password authentication. Without that limit, an attacker could trivially brute force their way into the system using those cross-origin requests. Beyond the gateway issues, the documentation from iSecurity regarding log poisoning vulnerabilities is equally concerning. Attackers are using Transmission Control Protocol port 18789 to inject indirect prompts into the OpenClaw logs. This allows them to manipulate the agent's behavior by polluting the very history it uses to make decisions. The situation is even more dire when you look at the Trend Micro report on Atomic Stealer malware. These payloads are being fetched from the Internet Protocol, address 91.92.242.30, through simple skill markdown files. It proves that the current trust model for agent extensions is fundamentally broken and insecure. Relying on these local agents for high-stakes work requires a level of isolation that the current architecture simply does not provide. When you have 3,505 skills available and dozens are known to be malicious, the risk profile becomes unacceptable. We are seeing a total failure in the verification process for these automated development workflows. This shift in how we handle agent security moves us from general development concerns to the very specific performance requirements of agents in high-stakes financial environments. If we are going to trust code to execute trades, we need the raw speed found in the asynchronous MetaTrader 5 library, named aiomql.
Modernizing the trading experience means moving away from the brittle scripts of the past. By wrapping MetaTrader 5 functions with this new framework, developers can finally use native Panda's technical analysis directly on candle and tick objects. It shifts the entire focus from managing data plumbing to actually refining the underlying business logic. We are seeing a real reduction in the friction required to launch a high-frequency strategy. The Forex symbol class handles the complex math of calculating pip values and trade volumes based on specific stop-loss distances automatically. It effectively eliminates the common human calculation errors that often lead to catastrophic losses in volatile markets. There is a sophisticated layer of discipline built into the core architecture through the risk management class. It enforces strict 1-to-3 risk to reward ratios and calculates position sizes without manual intervention. For a trading firm, this means their strategy is being executed with a consistent and predictable risk profile every single time.
Sloan, those automated guardrails are only as reliable as the underlying engine that keeps the connection alive. The real engineering hurdle here is that MetaTrader 5 is fundamentally synchronous. This library has to use asynchronous to thread calls to wrap every function, which prevents the main event loop from stalling during heavy input-output operations. Scaling this beyond a single instrument requires the bot process pool feature to run independent bots in parallel. By isolating MetaTrader 5 connections across multiple processes, you avoid the bottlenecks of a single-threaded approach. It is the only way to manage dozens of symbols simultaneously without experiencing significant execution delays or missed trade signals. I am cautious about the reliance on automated trailing stops through the scalp trader class during a network outage. While the framework provides persistent trade recording to structured query language light and comma-separated value files, these are reactive logs. They are a necessary fallback for auditing, but they cannot fix a trade if the connection drops. Maintaining state with the open positions tracker is a complex task when you are dealing with high-frequency entries. The architecture needs to remain incredibly lean to ensure that technical indicators like the relative strength index are calculated and acted upon in milliseconds. Any overhead in the Python wrapper could be the difference between profit and a loss. We are moving from the controlled engineering of private trading bots to a much messier reality in the cloud. The financial risks of a poorly secured bot are one thing, but we need to look at the massive billing risks now facing developers who expose their Google Cloud application, programming interface keys to Gemini abuse.
The financial fallout from these artificial intelligence security oversights is moving from theoretical risk to a literal business-ending reality for many firms. We are looking at a documented case where a standard monthly bill of $180 exploded into $82,314.44 in just 48 hours. This is not an isolated incident, because researchers recently found over 2,863 live application programming interface keys exposed within client-side JavaScript. For a small company, that level of unauthorized spending is a catastrophic event that can wipe out their entire operating budget before they even realize their credentials have been compromised. Beyond the immediate financial ruin, the exposure grants intruders access to sensitive data stored within the files and cached contents endpoints. It is a dual threat where your proprietary information is being harvested while you are simultaneously being billed for the privilege of that theft. The sheer scale of this vulnerability across the cloud ecosystem is staggering. The immediate priority for any technical team must be an industry-wide rotation of every legacy key currently in production. Because these keys were often deployed publicly long before they gained generative artificial intelligence privileges, they represent a massive ticking time bomb for organizations that have not audited their permissions. Vance, why is the default setting so permissive?
The core of this problem is actually a fundamental design choice, where Google Cloud sets new keys to an unrestricted status by default. This means that if you enable the generative language application programming interface on a project, every existing key suddenly and silently gains the power to call Gemini endpoints without any administrative notification or explicit permission. When you look at the recent scan of 250,000 Android applications, the data shows over 35,000 unique keys embedded directly into mobile code. It is clear that developers are still treating these credentials like static assets instead of dynamic secrets that require rotation. They are basically leaving the front door wide open for abuse. The retroactive nature of these permissions is what makes the situation so volatile for engineering teams trying to maintain a budget. You could have a key that was perfectly safe for simple tasks 5 years ago, suddenly becoming a gateway to massive compute costs today. It proves that a lack of granular control is a major liability. We are seeing that even when keys are used legitimately, the lack of oversight leads to massive fiscal leakage. Transitioning from the sudden costs of a security failure to the daily operational expenses of running a fleet of agents is the next logical step. Managing those rate limits and costs effectively is becoming a critical engineering skill.
Scaling a fleet of more than 100 automated agents reveals that providers like Anthropic apply rate limits across an entire account rather than individual keys. This structural bottleneck means that your entire fleet can stall simultaneously without a very sophisticated orchestration layer. It forces a move toward complex backend management of these resources. Beyond the technical throttling, the financial burden of high-performance models is reaching a breaking point for many startups. Running a top-tier model like Claude Opus can easily reach $3 for a single request when dealing with long conversation histories. Without proactive management, the dream of automated service turns into a nightmare. Modern observability for these deployments requires that engineering teams prioritize business metrics like lead capture and apology rates over traditional application performance monitoring tools. Standard dashboards like Datadog fail to capture the nuance of a failing conversation. It is no longer just about uptime, but about the quality of every interaction. Vance, I wonder if the technical trade-offs required to achieve this kind of efficiency are actually sustainable for most small engineering teams. It seems like a massive amount of custom plumbing just to keep the lights on without draining the company bank account in a single weekend of high traffic.
The most effective strategy involves a clever model routing system that utilizes Claude Haiku for aggressive summarization. By condensing long conversation histories before they hit the expensive models, teams are seeing a 70% reduction in input token volume. This allows them to maintain a fleet of 10 agents for $115. Maintaining reliability at this scale is a constant battle, usually fought with an agent mode degradation ladder. If the primary large language model application programming interface experiences an outage, the system automatically switches to rules-based or human modes. This prevents a complete service collapse during those inevitable technical failures and platform outages. I was actually quite impressed by the accuracy gains achieved through explicit anti-hallucination prompting techniques. Systematic error rates have dropped from 8% down to just 2% in 2025. It proves that you do not always need a bigger model. You just need better constraints on your prompting logic. As we conclude, we have seen that the collision of state-of-the-art research and the reality of production creates a massive gap. From accidental $80,000 bills to the precision of model routing, success depends on moving past the hype and mastering the underlying infrastructure and cost controls. While DeepMind achieves a Frechet video distance of 1.3 with unified latents, the production reality is much messier. We have watched thousands of exposed Google Cloud keys turn into massive financial liabilities. It is a stark reminder that even the most elegant video generation architecture cannot survive a basic failure in security credential management.
Vance, your focus on those security gaps highlights the core tension we have explored today. We are moving from the controlled beauty of research labs into the wild complexity of production agent fleets. This transition demands more than just sophisticated algorithms. It requires a fundamental shift toward rigorous cost controls and robust infrastructure to prevent these systems from failing. The future of engineering will be defined by how well we manage these invisible layers of risk and coordination. As we continue to push the boundaries of what these digital agents can accomplish, let us keep the human and financial costs in perspective. Thank you for joining us on the Dev Journal. We return tomorrow with more technical insights.